everybody. In this video, we're going to be talking about how to calculate at least one probability. So take 3 deep breaths and let's make this math easy. All right, so let's say that we were going to flip a coin 4 times and we wanted to find the probability of getting at least one head. So one way we could calculate this is we could make a choice tree to represent the sample space. So we could say when we flip the coin the first time, we have 2 possibilities of what our outcomes might be. We might get heads or tails. Then we flip it the second time, we'd have 2 options there. And when we flip it the third time, each one of those will have 2 options. And this might take me a minute to write out. But this would be the sample space after 3 coin flips. And then if I flip it again, then each one of these will have 2 options branching off of that. And so essentially our choice tree is going to have 16 different options. And if we wanted to, we could use this choice tree to list out all 16 of those options. So I've done that on the next slide. And our sample space, or the list of all of the possible outcomes when you flip a coin 4 times, is listed here. And so we have 16 possible outcomes. And if I want to get at least one head, this would be a favorable outcome. So with this and this and this and this and this and this and this, because all of these have at least one head. Some of them have 2 heads, some of them have 3 heads. This one up here had 4 heads, but all of these have at least one head. And so it looks like our probability would be 15 out of 16. Now, this wasn't terribly hard for this problem because flipping a coin only has 2 options. But if you were doing something like rolling a die 6 times or 4 times or whatever, that would be a sample space that you definitely don't want to have to list out. So we want to figure out an easier way to calculate the probability of finding at least one outcome. So another way that we can think about this is we can think about what the opposite of getting at least one head is. And if you think about the opposite of getting at least one head, that would be getting all tails. Because when you flip a coin 4 times, you'll either get at least one head or you'll get all tails. There's no other option. And so that means that getting all tails is the opposite of getting at least one head. And so we could calculate this and we could say, well, the probability of at least one head, this would be equal to 1 minus the probability of all tails. And so the way that we could calculate this probability is we could say, well, 1 minus the probability of all tails. Well, I know that the probability of getting all tails is going to be 1/2 times 1/2 times 1/2 times 1/2. Because I have to get a tail on the first one, a tail on the second, and a tail on the third, and a tail on the last one. So that's the probability of getting all tails, which you could simplify to be 1/16, because there's a 1/16 chance you'll get all tails. And if you're going to subtract the fractions, you have to get common denominators. So you'd write it as 16/16 minus 1/16. And you can see that this is the same answer that we got by listing out the sample space. But this method will be way easier, especially if you have a sample space that's much bigger. Like for example, if you were going to roll a die like 3 times or something, and you wanted to find the probability of getting at least one, 4 or something like that. It would be way easier to calculate it out with this type of a calculation rather than having to list out the entire sample space. So the general formula for calculating at least one types of probability is that the probability of getting at least one outcome is 1 minus the probability of getting none of them. So when we calculated out the probability of getting at least one head, the way that we calculated that out was by doing 1 minus the probability of getting no heads. And we wrote it down as the probability of all tails, but no heads and all tails is the same thing. So this formula will make it much easier to calculate the probability of getting at least one outcome. And this idea is very, very similar to what we did in the counting methods video, because the 1 is basically like 100%, or like it's including all of the possible outcomes, and then you subtract the probability of getting the outcomes that are not what you're looking for. So in the counting methods video, we looked at the number of ways you could build a committee so that you had at least one female on the committee, and we figured out the total number of ways you could build the committee, and then we subtracted the number of committees that were all male. And so we basically took all of the options and subtracted the options that were not what we wanted, and that gave us the number of options of what we did want, which was having at least one female on the committee. And this idea is very similar. It's just kind of like a probability version of it, because you take a 100% chance probability and you subtract the probability of getting what you don't want. And that will give you the probability of what you do want, which was at least one head. So let's do another example of this. Let's say that you are going to draw 3 cards without replacement from a standard deck of cards, and you want to find the probability of getting at least one ace. Well, the way I want to think about this, because I definitely don't want to draw out the choice tree, is I'm going to say, well, this is going to equal 100% probability minus the probability of getting no aces, because getting no aces is the opposite of what I do want. And so I'd say, okay, well, what's the probability of getting no aces? Well, the probability of getting no aces is going to equal, for my first card that I draw, I have 52 options, and the number of those cards that are not aces is 48, because there are 48 non-aces. Then, for my second card that I draw, if I'm not replacing it, I will have 51 cards to choose from, and 47 of them will not be aces, because remember, you assume that you drew what you wanted to the first time. So I draw a non-ace, which leaves 47 non-aces, and then for my last card, I'll have 46 non-aces out of 50 cards total. So I'll calculate out what that would be, and when I multiply 48 times 47 times 46, I end up with the number 103,776. And when I do 52 times 51 times 50, I get 132,600. And when I divide those two numbers, 103,776 divided by 132,600, that gives me the decimal 0.782, etc. I'll just leave it like that though. And when it's in decimal form, that's really easy to subtract from 1, because remember, this is the probability of getting no aces. So it's about a 78% chance that when you draw 3 cards, you'll get no aces in those 3 cards. But the probability we were asked for is the probability of getting at least one ace. So I'm going to take 100% of my probability and subtract the probability that I get no aces, which is about 78%. And when I subtract that, the probability that I end up with is about 22%. So the probability of getting at least one ace would be 21 or 22%. And you can also do this type of idea with percentage probabilities. So in a large population, 82% of the people enjoy their job. And if 7 people are randomly selected, what is the probability that at least one of them likes their job? So the way that I would calculate this one is I would say the probability of at least one liking their job, that would equal 1 minus the probability that none of them like their job. So say none like their job. And I need to figure out what that is. So to figure out what the probability of none of them liking their job, so I'll say probability of none, I need to say, okay, well, if 82% of the people enjoy their job, then that means that 18% of the people don't. Because if 82 do, then the other 18% will not. So if I want to find the probability that none of the 7 people like their job, then I'm going to say, okay, well, I have 18 out of 100% for the first person not liking their job. Then I have 18 out of 100 for the second person not liking their job. Because remember, these are percentage measurements, and in a large population, the percentage isn't going to change very much if you take like 1 or 2 people out of it. So that's for my second person. Then I'll have 18 out of 100 for my third one. My fourth one is also 18 out of 100, and 18 out of 100, 18 out of 100, and 18 out of 100. So if I multiply all of these together, that's going to give me the probability that if I choose 7 people, none of them like their job. So I'll go ahead and calculate that. And when I do that, I get the decimal 0.000006122, etc. And the reason why this decimal is so small is because most of the people do like their job. And so the probability of choosing 7 people where none of them like their job is not very high, because that most of the people like their job, and if you're choosing 7 people, that's quite a bit of people, and it's pretty likely that at least one of them will like their job. But there is a small probability that none of them will like their job. And so to find the probability of at least one person liking their job, you're basically going to do 1 minus that decimal. So this is going to equal 1 minus that decimal that I just found. And when I subtract that, I get the decimal 0.9999938, etc. And so it's like 99.999387 whatever percent likely that if you choose 7 people randomly, at least one of them will like their job. So that's how you calculate at least one probability. If you have any questions, let me know. And I hope you guys have a great day.